And we will be moving on to our next speaker. Our next speaker is Corrine Yap. She is a PhD student at Rutgers University doing research in probabilistic combinatorics. She received a BA in mathematics and theater from Sarah Lawrence College, and she studied math in Budapest and theater in Moscow. In 2016, she first performed her original one-woman play called Uniform Convergence, and since then, Corrine has performed at over 15 venues, including the National Conference MAA Math Fest and Off-Broadway. Today, she will be discussing probabilistic combinatorics and mathematical theory. So yeah, without further ado, Corrine.
Thank you so much for that wonderful introduction, Catherine. And thank you, Dr. Kitchler, as well for, I was watching most of your talk on YouTube and just joined. And it's interesting you ended by talking about this interplay between algebra and geometry and the relationships between math and physics. And I'm going to kind of continue that theme and talk about the relationships between different areas, both within math and outside of math. So let me go ahead and start sharing my screen. Okay, let me see if I can make it full screen. Can you give me a thumbs up if you can see it, Catherine? Great, thanks. So the title of my talk is Crossing Disciplines, Probabilistic Combinatorics and Mathematical Theater. So I will talk about both of these things. I'm going to start by saying a little bit about what combinatorics is, which is a specific area of mathematics. And then I'll go into specifically what is probabilistic combinatorics, which is the area where I currently do research as a graduate student. And then we'll do a little bit of math. And at the very end, I'll discuss kind of how I came to study this area and a different aspect of my life that's mathematical theater. And I'll try and also keep track of the chat in case people have questions during the talk. Please feel free to stop me at any point if you have any questions. Okay, so first of all, what is combinatorics? I imagine that not everybody has heard of this word or knows what it means. Roughly, it's the study of discrete structures. So in the last talk, Dr. Kitchler was talking about different number systems, like the real numbers and the complex numbers. So those are both examples of kind of continuous structures, because you can think of the real line, the set of real numbers, as being continuous. From the interval like 0 to 1, there are no gaps in the numbers between 0 and 1. Whereas when we're talking about a discrete structure, you can think about the integers instead. So you have 0, 1, 2, 3, and you have kind of gaps between them. So another name combinatorics goes by is discrete math. Some people think discrete math is kind of a broader area that includes words like graph theory and algorithms and computational complexity. It's very much related to computer science. But let me give you some specific examples of what problems we're interested in combinatorics. The three most common broad problems are counting, existence, and optimization. So counting is probably if you have encountered combinatorics anywhere in your life, you probably first learned about it through a counting problem. The sorts of problems that you might learn in like a pre-calculus class. How many 7-digit phone numbers are possible? What if none of them begin with 0? So to solve this problem, you think about like, okay, well, for each digit, I have 10 possibilities, 0 through 9, and I have 7 digits. So I should multiply 10 times 10 times 10 for each of the 7 digits. So my answer would be 10 to the 7th. And then what if none of them begin with 0? Then I have to think like, okay, for the first digit, I only have 9 possibilities, and for the rest, I have 10 possibilities. So in general, we're interested in these kind of basic counting problems. How many of something can we find? Existence problems are asking like, does a particular type of discrete structure exist? Can we say like, okay, we want this thing that has these nice properties. Can we construct it? So an example of a problem here is if you have a set of medical students, there's what's called the kind of national residency, matching program where each medical student gives a ranking for their preferences for hospitals that they want to be matched at for the residency. And then the hospitals also need to choose which students they're going to accept. So a question you might ask is, does there exist a good assignment of students to hospitals? And you can give a list of like qualities that you want to define good. And this is actually a pretty famous problem in combinatorics that's called the stable matching problem. But the algorithms that have been developed to solve this problem have this very specific application in this residency matching. And the last type of problem is optimization. So given a set of cities and highways between them, what's the shortest route that visits each city exactly once? So that's an example of this problem. Here, we're not just looking at any old route. We want to find out what is the best route. So another famous problem in this area is something called the traveling salesman problem. So that problem asks, like, what's the shortest route that visits each city exactly once and ends where it started? And this is a famous example of something that's a very computationally difficult problem. So this is a brief overview of the types of things we're interested in within combinatorics. But in the pure math discipline, we look at problems that kind of have these applications, but we're not studying the, typically we're not studying the applications themselves. We're really studying like the structural properties that are underlying these problems. And then when we kind of can prove things about the more abstract structural concepts, then we say like, okay, we can take this result we've proven and apply that to this cool problem. So now let me go into, let me do a little bit of a deeper dive into one of these types of problems. Let me talk about an existence problem. So here's an example of an existence problem. Suppose you have a party where every pair of people is either friends or strangers. And let's just make this easy on ourselves. We're not going to consider like casual acquaintances or anything in between. We're either friends or you're strangers. How many people need to be at the party to guarantee that there are 3 who are all friends or 3 who are all strangers? So this is a problem that I want to model using a discrete structure. And the structure that I'll use is a pretty common one used for these types of problems called a graph. And it's not a graph that you learn about like, you know, in calculus and algebra classes. In combinatorics, when we talk about graphs, we're talking about a set of nodes and edges connecting those pairs of nodes. And here, I'm going to have the nodes representing the people at the party, and I'm going to put an edge for each pair of people. So here's an example of a graph. So here I have a party with 5 people at it, A, B, C, D, and E. And I've just put an edge to denote, you know, every single pair of people that's at the party. And I want to distinguish between which pairs are friends and which pairs are strangers. So in order to do that, I'm going to color my edges 2 different colors. I'm going to say that an edge is blue if it's between a pair of friends, and red if it's between a pair of strangers. So maybe my party looks like this. So A and B are friends, B and C are friends, or sorry, A and B are strangers, B and C are strangers, but A and C are friends. So now my original question about having a party and guaranteeing certain sets of friends or strangers at a party has become this purely mathematical question, which I can write in this way. How many nodes should there be to guarantee the existence of either a blue triangle or a red triangle? Right, the way that I've colored this, a blue triangle represents 3 people who are all friends, and a red triangle represents 3 people who are all strangers. So I've just rewritten my original question in terms of this graph that I've colored for you here. And as you can see, 5 isn't enough, because if you look at this coloring that I have, I don't have any red triangles or any blue triangles. You can check every single triangle, for instance, A, B, C, right? There's a red edge and there's a blue edge. And then B, D, E, there's 2 blue edges and a red edge. If I look at every single triangle, I'll see that none of them are all red or all blue. Okay, let me give you another example though. Here's a party with 6 people. And I've just, you know, kind of arbitrarily assigned some blue edges and some red edges to denote friends and strangers. This one does have some red and blue triangles in it. That's one example. There are several others. For instance, FJH is a blue triangle. So it turns out here for this specific party, there is a set of 3 people who are all friends, and there's a set of all 3 people who are strangers. Was this a coincidence? Did I just kind of get lucky with the way that I colored the edges? It turns out the answer is no. 6 nodes suffice always. So what this theorem says is no matter how the 6 people arrive at the party, no matter how which one of them is friends and which pairs are strangers, if you have 6 people, there will always be either 3 who are friends or 3 who are strangers. So in other words, what that means is that in any coloring of this graph on 6 vertices, in any way that I assign the edges either red or blue, I will always get either a red triangle or a blue triangle, or both. But on the flip side, 5 isn't enough. So we saw in the previous picture that we can have a party of 5 people where no 3 are all friends or no 3 are all strangers. And this problem is kind of the foundations of an area in combinatorics called Ramsey theory, where the motivating question is, given a structure, some type of discrete structure, how large does it have to be to guarantee I get these kind of nice, organized substructures in them? So in this particular example, I'm looking at how big does my graph need to be? How many nodes do I need to have in order to guarantee these nice, what are called monochromatic structures? So all red or all blue. But graphs aren't the only things you can ask these questions about. You could also ask the same things about, sets of numbers, if you're coloring sets of numbers, or if you're familiar with what vectors are, vectors in a vector space. So there are all sorts of different objects that you could ask this type of question about. Okay, so this was an example of kind of a typical combinatorial problem. Let me now talk about what probabilistic combinatorics is. So what we do is we take the 3 types of problems, the counting, existence, and optimization, and we introduce randomness in some way. And why do we want to do that? Well, there are kind of 2 different ways that we'd like to introduce randomness. One is that we study random variants of discrete structures. So we take things that we study in combinatorics, like graphs or matrices or walks, and we put the word random in front of it. Random graphs, random matrices, random walks, and we study those objects instead. And why would we want to do this? Well, an example of a problem where you'd want to use a graph is if you're modeling social networks. Right? Say you want to construct a graph that represents all of your friends on Facebook and all of their friends and all of their friends. You could have the nodes represent the people on Facebook and the edges represent, if you're friends or not. And if you want to say something, if you want to kind of simulate a typical social network and say something about what social networks look like in general, it might not be enough to just look at your personal social network, right? Because that could look a lot different from someone else's social network based on, how old you are, or how many people you know, or what types of things you're interested in. So in these types of problems, we instead want to study like random networks, because then we can say things like, on average, a social network might look like this. It might be this connected, or it might be this dense. So that's one way of kind of injecting probability into these types of problems is by just kind of looking at random variants of things. Another way is to study deterministic structures, so non-random structures, but use probability to find solutions. And I want to talk about this part a little bit more. So essentially what we do here is we translate the statement, there exists something, to the probability of something is greater than 0. And this is kind of a vague description, so let me give you a more specific example of what I mean here. So we're going to get into a little bit of math. So if you've seen probability before, some of this will look a little bit familiar to you, but if you have not seen any probability before, then don't worry too much about it. I will let you know which things you can kind of gloss over and not pay attention to. Okay, so let's go back to this party problem and change the numbers. How many people do we need to guarantee now that there are 10 at the party who are all friends, or 10 who are all strangers? That's a lot bigger than 3. Now we're looking at 10 people who are all connected by edges that are all the same color. And I just want to know, like, let's make a guess, 100. Is 100 people going to be enough? So to solve this, we want to look at a graph on 100 nodes now. Is there a way to color the edges red and blue so that no set of 10 people is monochromatic, which means they're all friends or all strangers? So if you were to do this in a way that we kind of tackled the earlier problem with just 5 nodes, then the sort of brute force way to do it would just be to like run through all the possible ways to color this graph on 100 nodes. But there are going to be a lot of edges in that graph, and it's going to take a computer ages to run through all the possible colorings, and in each coloring, look for all the sets of 10 people and figure out if they're monochromatic. Because again, this is an existence problem. We want to prove that there exists a coloring where we don't have these monochromatic subsets in it. So in order to show something exists, then the kind of naive way to approach it would be just like, okay, let's find one. Let's find a coloring. So instead of trying to just brute force the problem, I'm going to try this clever idea of doing a random edge coloring. So for each pair of people, I'm going to flip a coin. And if the coin is heads, I'll color the edge red. If it's tails, I'll color it blue. And then I want to look at, okay, what edge coloring will I get out of flipping coins? Well, let's look at a specific set of 10 people. Let's ask, like, is it likely that they're going to be monochromatic, that they're all going to be friends just from flipping coins, or that they're all going to be strangers just from flipping these coins? So I want to calculate this probability. What's the probability that they're all friends? Well, I have 1/2 probability that my coin will land heads for each pair of friends. And there are 10 choose 2 pairs. So if you're familiar with this notation, then 10 choose 2 is something called a binomial coefficient. It represents the number of ways to pick 2 people out of 10 people. If you're not familiar with this, don't worry about it. It's just the number of edges that's among this set of 10 people. And I've calculated it out for you. It's 10 choose 2 is equal to 45. So there are 45 edges, and each of them needs to come up heads. So the probability that all of them come up heads is 1/2 to the 45. Then I look at, what about if they're all strangers? Well, now each of my coins needs to come up tails. So again, I have the same probability. I have 1/2 to the 45. So if I want to look at the probability that they're either all friends or all strangers, I just add these two together. And I say, like, okay, the probability that this specific set of 10 people is monochromatic is 2/2 to the 45. Okay, so where is this going? Well, let's look at the total number of monochromatic 10 sets I have in my graph. So I have my random coloring, and I want to count how many 10 sets there are that's monochromatic. But this is a random graph, right? So I can't just like go in and count them, because anytime I run my experiment again, I'm going to get a different number, right? Anytime I do new coin flips, then X is going to change. So really what I want to know is, what's the average value of X? If I do my experiment a bunch of times, on average, how many monochromatic 10 sets can I expect? And so this is where, if you know probability, you might know where this expression comes from. The expected value of X is equal to this. If you don't know probability, I'll mainly just black box it. So 100 choose 10 represents the number of sets of 10 people there are in this graph. And I'm multiplying it by 2/2 to the 45, which is the probability that a specific 10 set is monochromatic. So that's just using this thing called linearity of expectation. I can add up a bunch of expected values. I won't go any more into it, since, you know, if you don't know probability, then this will just be a way I calculated expected value. And if I calculate this out, this ends up being about 0.49, which is less than 1. Okay. So why do we care about this? Well, this is where the Erdős Magic happens. I mentioned this in my abstract, that the probabilistic method is also called Erdős Magic. This is an average. And since the average is less than 1, what do we know about averages? If you think about just like an average of a set of numbers, then the property, the the meaning of it being average is that there's something that's at most the average and there's something that's at least the average, right? Because you're thinking about it as kind of the middle. So what I've told you is that the average value of x is less than 1. And x has to be an integer. It's counting a number of sets. So that means that there is a coloring where x is at most the average, and there's a coloring where x is at least the average. But if there's a coloring where x is at most the average, and the average is less than 1, right, the biggest integer that's at most the average is 0. So by this property of averages, I can say that there's a coloring where x is equal to 0. But what is x? It was the total number of monochromatic 10 sets. So there's a coloring where the number of monochromatic 10 sets is 0. And now let's think back to what we wanted to show. Remember, we wanted to show that there exists a coloring where the number of monochromatic 10 sets is 0. We're 10 people. There aren't 10 people who are all friends or 10 people who are all strangers. So it turns out that 100 is not enough to guarantee that there are 10 who are all friends or 10 who are all strangers. So what happened here? We didn't construct a coloring. I can't hand you the which coloring I'm talking about. I'm saying that there exists a coloring where no 10 people, there exists a party where for every set of 10 people, they're not all friends and they're not all strangers. But I haven't told you what this party looks like whatsoever. I've just told you that I know it exists somewhere out there in the ether. And so this is where I guess the magic part comes in. And it's called Erdős Magic because it was coined, this method was formulated by a famous mathematician named Paul Erdős, who he was very prolific, and he's one of the most famous mathematicians, and particularly in combinatorics. Let me take a look at the time. All right, great. So anyway, let me just say that there was nothing special about 100 or 10. So I can replace those numbers with variables to get a theorem, which just replaces the number 100 with n and the number 10 with k. And I have essentially given the same expression that I had for the expected value here and said, if this expression is true, then there is a way to color all the edges among n nodes so that no set of k nodes has all monochromatic edges. So this problem had nothing to do with probability, but by introducing randomness, we could use tools from probability to get a solution. So for me, the reason I study, the reason I became fascinated with this magical idea and with probabilistic combinatorics is we're taking two areas that don't really seem to have anything to do with each other, and we're using tools from one area to solve problems in a different area, right? If you looked at this problem, you wouldn't think that randomness would have anything to do with solving the problem, but somehow by imposing this random structure, we end up getting this really powerful and really sort of magical result. Okay, so in the few minutes that I have left, I want to, so that was a lot of math, so it's okay if you didn't totally follow everything. I want to pivot away from doing math and talk more about, my life with math, and the second part of the title, which was mathematical theater. So I talked about how I enjoy, kind of crossing disciplines within math, but I also want to talk about how I've used math in other areas of my life, and in particular, mathematical theater. So I have written and performed, as Catherine said in the introduction, a one-woman play called Uniform Convergence. And I have the synopsis here, but I'll summarize it. It's a one-woman play that's about the stories of two women. The first is of historical Russian mathematician Sofia Kovalevskaya. And she really faced a lot of, difficulties due to sexism in trying to really become, trying to get her name out in the math world at the time in late 1800s Russia. And the second is of a fictional Asian American woman known as the Professor. and she is teaching an introductory real analysis course and uses math concepts to draw parallels to race and gender conflicts she encounters in society. So I wanted to end by playing a clip, and then I'll say a little bit after the clip, but it's only a couple of minutes. I think that would be better than me trying to verbally describe the show. So let me share computer sound and play this clip.
Take the human life, for example. It's a continuous thing. It's impossible for life to be discontinuous because it only continues until you die, and it doesn't pick up again from where it left off. On this earth. But my life is most certainly non-uniformly continuous. If you let delta be some span of years, say from when I was 8 to when I was 15, in order for it to be uniformly continuous, then for any span of years or months or days between ages 8 and 15, you should be guaranteed to find a value which that time span is approaching. In a normal life, one could define that value as puberty, as 8th grade graduation, as acing next week's history test, any of the trivialities that we set as our goals for however long they're relevant. But for me, my trajectories are always interrupted. Never as simple as they initially seem. When I was 15, I wanted to be an actress. The next year I was cast in the school musical as a Chinese man named Chang. It's the melanin. It's the extra molecules of melanin in my blood that manifest themselves into these societal barriers, into the discontinuities, into the jagged lines and the rough edges that make every beautiful continuous function into a hideous conglomeration of edges and vertices. It's the straight black hair and the dark brown eyes that create these extremal points, these suprema and infima, the small stature and the last name that prevent every span of time from having a predictable endpoint. Because if you pick out an epsilon, I can't always give you back a delta. I fell in love with a blonde boy with green blue eyes whose laugh made me drunk on California sunshine. We stood side by side and the mirror told me that his skin was darker, but according to everyone else, I was the colored one. Let f be a function mapping the imaginary to the real. If x and y are points in my imaginary world that are so close together they look like they touch, then when are there analogous values in the real world close enough to occur with an epsilon equals the span of my life?
Guess I chose to end on a rather dramatic note. But since I'm almost out of time, I won't share my last slide, which is I'll just say it out loud. So that was a clip from my show. And the takeaway that, or I guess what I want to tell you about it is that math doesn't exist in a void. Right? We bring, as mathematicians, we bring our identities, our perspectives, our experiences into the room when we do math. And for me, that was a really important realization that I had when I tried to merge these two interests that I had, math and theater, and didn't think that it was ever something that would happen. But, you know, the math community has been really accepting and supportive of this play, which I didn't realize at first. I wrote it before I entered grad school and kind of put it away for a while until I realized that it was something that my friends in graduate school and people at other departments were interested in. And it's led me to meet and have a lot of really wonderful people and have a lot of really amazing discussions about things that I really care about within the STEM community, which is diversity, which is making our departments and our classrooms more welcoming and creating a welcoming environment for students of all backgrounds. So that is to say, I encourage you to not forget about who you are and what you love, even if you do choose to pursue math, even if you decide that you want to major in math in college and go on to graduate school, or if you decide to go into industry, or if you don't do math at all. Just remember that math is a place where you can go and still be who you are and still have your other interests. And I would encourage you to pursue whatever it is that you're passionate about. So I think I'll end there. Thank you.
Thank you so much for sharing, Corrine. Does anyone have questions for her?
So I got a question in the chat. Have you used probabilistic combinatorics with computer science? So I haven't, but I have several colleagues who do. So in fact, in my kind of research group amongst graduate students, about half of us are pure math and half of us are computer science. And we do like reading seminars together and talk about papers. Yeah, it's not something that I have personally done, but there are a lot of people who dabble in both fields.
And there's another question in the chat asking what inspired you to write Uniform Convergence?
So I started writing it when I was a sophomore in college, and it started out as a history play for a playwriting class. And I was like, oh, this is my chance. I can write about a mathematician and finally like merge math and theater. So I started writing about Sofia Kovalevskaya, who has a really fascinating life. If you ever, need something to read, go look her up. But at the same time, I was taking a real analysis course, which is the course that is kind of the premise of the show. And there were a lot of things happening on my college campus that I felt really strongly about with regards to students of color and with regards to opportunities for students. And that inspired me to start writing this second character, the professor, kind of based on my own opinions and my own experiences. And over the years, it just sort of evolved from there. And at some point, these two characters kind of decided to coexist in the same world. And that's when Uniform Convergence happened.
And I had another question. Are you still performing this?
Well, not currently because of COVID. I had a few performances that were canceled at the end of the spring semester. But once we are back in person, I will be performing. I have a few performances, like every month or so. Yeah. So if you are at an academic institution, I performed at colleges and high school programs and all sorts. Feel free to invite me. I don't charge. I also have, if you are interested, I don't have a video publicly available because I don't have one that's like of high quality. I have some from just like various performances. So if you're interested, you can message me or email me. I think my information is I'm on the Slack site and I can send you a link.
Thank you so much.